Hey there! Today we're going to do our last straightforward lesson on functions. Today we're doing inverse functions, and most people find this extremely doable, and they really remember it well from Algebra 2 also. So we've got 5 different objectives. We are going to write the equations of inverse functions. We're going to algebraically verify that 2 functions are inverses. We're going to look at the numerical and the graphical links between functions and their inverses, and we're going to determine whether an inverse function exists. So when we were in Algebra 1 and even pre-algebra, you learned to use the idea of inverse operations in order to isolate x. I'm going to draw a parallel to what we're doing today. So I know, for instance, on this first equation, that if you want to isolate x, it's x plus 6. So the opposite of adding 6 would be to subtract 6, right? And when you do that, you isolate x. Of course, I know that you know how to do these equations. For instance, on the fourth one, if you have x divided by 2 equals 9, dividing by 2 is the inverse operation to multiplying by 2. So you know we can multiply both sides by 2, and that serves to isolate x. That's where we're headed when we look at inverse functions. So keep that basic idea in mind. Now, I want to show you how inverse or how 2 functions can be proven to be inverses algebraically. So we compose the 2 functions. So what I need to do is I need to say a of b of x. And when I apply inverse functions to each other, it's going to serve to isolate x. So in equation solving, you apply inverse operations to isolate x. With functions, you apply inverse functions to isolate x. So remember, this is a 3-step process. First, what is b of x? So show me what your interior function is. Second, show me what it looks like to insert or to set up the equation when I take 3x minus 15 into a of x. Well, a of x takes any input, multiplies the input by 1/3, and adds 5. So when I distribute, I get x minus 5 plus 5, and it felt effortless to isolate x. That's the deal with inverse functions. If it doesn't work out smooth as silk, if you feel like you're having to kind of force it, then you don't really have a pair of inverse functions. So it needs to just work out what feels like effortlessly. Well, I'm only halfway done. I also need to do b of a of x. So step 1, what is the interior function? Well, it's 1/3 x plus 5. Step 2, what's it look like to insert anything into b of x? Well, you're supposed to say 3 times whatever your input is, and then minus 15. Now let's clean that up. So when I distribute, I get x plus 15 minus 15, and again, I isolate x. So because a of b of x equaled b of a of x, and they both equaled x only, they are truly inverses of each other. So again, we've just learned how to algebraically verify that 2 functions are inverses. So I'm going to do c of d of x the same way, and again, it should feel effortless. So step 1, tell me what the interior function is. What is about to be plugged in? Step 2, show me what it looks like to plug anything into c of x. Well, it's supposed to be 2 times whatever my input value is. I'm supposed to take that input value to the 5th power and then subtract 8. Well, I know if I take a 5th root to the 5th power, then I simply am left with what's under the radical. Now when I distribute, I get x plus 8 minus 8. And again, I'm getting x, and it felt effortless. So I'm 50% sure that these are inverses of each other. I need to be 100% sure, which simply means I need to do d of c of x as well. So this time my interior function is 2x to the 5th minus 8. Also, let's see here. When I do d of anything, I have to say the 5th root of 1/2 times that anything that I'm inserting. And then I need to add 4. So let's see how that works out. Now under the radical, when I distribute the 1/2, I get x to the 5th minus 4. And then I've got that plus 4 at the end. Well, the 5th root of x to the 5th, sure enough, equals x. So guys, again, since c of d of x and d of c of x are both equal, and specifically they equal x, I have now algebraically verified that c and d are inverses of each other. So we have done one objective, all right? So there are other ways to verify that a pair of functions are inverses, and sometimes another method might work better for you, which is why we need multiple ways. It depends on how easy the equations are to insert into one another, whether you want to go about it algebraically. But if it says to verify algebraically, then there's work for you to show me. It may say verify it graphically or numerically, and that's a different strategy, okay? We'll get there. Now, there are some functions that you don't need to work really hard in order to find their inverses. And what you're saying right here are some of those. So, like, it's easy for me to see that on k inverse of x, if k of x takes the input value and multiplies by 3, then k inverse of x ought to take the input value and divide by 3. And I could write it x over 3 or 1/3 x. Those are equivalent, okay? So if it's a one-step operation kind of function, it's really easy to see the inverse. Likewise, if m of x takes the input value and subtracts 9 from it, then the opposite idea would be to take the inverse, the insert value, and add the 9 to it. So it would simply be x plus 9. It's a one-step operation. Now, n of x uses your input value and takes it to takes the 7th root of your input value. Well, the opposite of taking the 7th root of an input value is to take the input value to the 7th power. All right, so let me go ahead and mention a lot of people will just do a knee-jerk reaction on u inverse of x and go, oh, well, the opposite of 4 to the x is x to the 4th. No. Because remember, the opposite of taking something to the 4th power would be to take the 4th root, and that would have to be your u of x. That is not what I gave you for u of x. That means your u inverse of x is not correct. So we need to fix this problem. So that's a lot of times what people will do is they'll just say, oh, I'm just going to kind of reverse the place of the base and the exponent. Now, if you think back to your Algebra 2, when you all started doing exponentials, do you see that u of x is an exponential function because the x is in the exponent? Do you remember what you did alongside exponentials? If you are answering logarithms, you're right. So the inverse of an exponential is a logarithm. What kind of logarithm? Well, since the exponential has a base of 4, the logarithm should also have a base of 4. So the inverse of 4 to the x is log base 4 of x. Now, on v inverse of x, you've got the same scenario. So v of x is a logarithm. So I already know its inverse is an exponential. Do you remember that ln x simply means log base e of x? We don't write log base e of x. We write ln of x. But log base e of x is the meaning. Well, now I know that v inverse of x is an exponential, and the base of the logarithm and the base of the exponential must match in order for me to have a pair of inverses. So my base has to be e to the x, okay? And so that's just a quick rundown of finding the equations of inverse functions. But now the question is, can I get the slide to turn? The question is, well, how do you find the equations of inverse functions if it's not just a single operation kind of function? Well, there's a real easy process, and I bet the minute we do this, you're going to go, oh, I do remember this from Algebra 2. Well, here's the nitty-gritty. Sub in y into the f of x or the g of x or h of x. That's an easy step. It is easier to manipulate with y than it is to manipulate with the h of x or g of x or f of x notation. So we just make the problem a little easier to manage. Now here's what you need to know about inverse functions. Inverse functions are simply reversing the x's and the y's. That is all there is to it. So in the equation, I'm going to simply reverse where the x's and the y's are in the equation. So I have now begun my inverse. What I need to do is I need to isolate y now. So it would be 3y equals x plus 8. When I say y equals x plus 8 all over 3, that's not the way we see that written. We see it written 1/3 x plus 8/3, so that we say that this inverse is it's just a line. The inverse of f of x, which is linear, is a brand new line. Now I know that my line, remember this is just going to be a line with a positive slope. I know it's going to pass the vertical line test. So I need to not just say it's an inverse, I need to say it's an inverse that is a function. So you might just not have caught the significance of what I've said. You can always find inverses, but your inverses may not be functions. If they are functions, give them a function title. So the title on this one is f inverse of x. If they're not functions, then you just leave y in the equation. So on g of x, I've already subbed in y. I'm going to reverse x and y. So now I'm going to begin to isolate the new y. So I cube both sides, and I add 6. Now I know that x cubed plus 6 looks basically like this. That's the shape of it, and I know it's been elevated 6 units on the y-axis, but I know just by looking at it, it is going to pass the vertical line test. Therefore, g inverse of x is x cubed plus 6. I determined that the inverse equation that I came up with is a function, so I give it a function name. See, this isn't bad. I bet you do remember this. Now, on h of x, we need to talk about this one because this is going to come up more and more frequently in your equation solving. And when you first see it, people kind of freak out a little bit. But by the end of precalculus, this will be such a natural progression. You won't be bothered by it at all. So the first thing I'm going to do is say, all right, my y needs to be switched to an x. And then all my x's need to be switched to y's. So I've just enacted the inverse. Remember, inverses do nothing more than switch x's and y's. Now, I need to clean this up. So the easiest way to clean it up is to go, okay, I'm going to cross multiply. So y equals xy plus 4x. All I did was cross multiply there. Now I need to solve for my new y, but this is where it gets tricky. How do you solve for y if there are two y's in the problem? The y has to be y equals something with nothing but x's in the answer, and right now I've got y equals xy plus 4x, so that can't stand. Well, guys, group all your y terms on one side of the equal sign, leave your basic x terms on the other side of the equal sign. And if I've got two y's on the left-hand side, but I want to isolate a single y, I factor the y out like a GCF. So y equals 4x over 1 minus x. Now, depending on which way you had cross multiplied first, you may have gotten this answer, negative 4x over x minus 1, where every sign of every term in the first fraction is reversed. So that would also be a correct answer. I would accept either one of them. So those are both just basic rational functions. I'm not going to graph it right this minute, but just trust me that it is a function that passes the vertical line test. So I need to say that h inverse of x is equal to negative 4x over x minus 1. or 4x over 1 minus x. Either one is perfectly good. You need to put down one of them. So guys, when I go back to my list of objectives, I have just learned how to write equations of inverse functions. So now what we're going to do is we're going to look at numerical and graphical links, okay? So it's so easy to verify that your answers are correct that what we want to do is we want to look at verifying your answers in multiple ways. Now we've already said we know how to verify algebraically. So a minute ago I gave you f of x is 3x minus 8. And I think that we got that f inverse of x is 1/3 x plus 8/3. Let me go back and see if that's what, make sure I'm not messing that up. Yep, we got 1/3 x plus 8/3. So I am going to say, well, I know algebraically f of f inverse of x is what I need to do. I need to show that that smooth as silk works out to x. So my interior function is 1/3 x plus 8/3. If I want to plug something into f of x, I say 3 times that something I'm plugging in minus 8. I distribute. I get x plus 8 minus 8. Man, smooth as silk, guys, smooth as silk. If I get x with almost no effort, then you know truly you have found a pair of inverse functions. I'm 50% done. I need to be 100% done. So I go the other way. This time my interior function is 3x minus 8. Whenever I plug into f inverse of x, I say 1/3 times whatever I'm plugging in plus 8/3. I distribute. And then the negative and positive 8/3 cancel. And so once again, I have just gone through how to quickly algebraically verify that f of x and f inverse of x are truly inverse functions. Now, I can show you the exact same thing for g of x and g inverse of x, but I have a feeling you might like me to skip this algebra. I bet you feel pretty comfortable with it. And let me use g of x and g inverse of x to verify in different ways. All right, so we're going to look at the numerical connection and the graphical connection between a pair of inverse functions. So what I've done is I've set up t-charts for both g of x and g inverse of x. I've also thought, well, if I'm going to take cube roots, it would be nice to take cube roots of numbers that work out real nice and neat because I'm going to plot points later. So I know it's easy to take the cube root of 0. It's easy to take the cube root of 1 and negative 1. It's easy to take the cube root of 8 and negative 8. So I've chosen x values on my purple t-chart that will allow me to take the cube root of those easy values. So when I plug in negative 2, this causes me to take the cube root of negative 8, and that is negative 2. When I plug in 5, this causes me to take the cube root of negative 1, which is equal to negative 1. When I plug in 6, I'll be taking the cube root of 0, which is 0. When I plug in 7, I'll be taking the cube root of 1, which is 1. And when I plug in 14, I'll be taking the cube root of 8, which is 2. So when I build a t-chart for weirder functions, I'm strategic in my choices of x because then I don't get so bogged down. The t-chart doesn't take as long. I don't need my calculator in order to get decimals, and I don't have weirdo points to plot. So let's do the t-chart for y equals x cubed plus 6. So let's see here. Negative 2 cubed is negative 8, plus 6 is negative 2. Negative 1 cubed is negative 1, plus 6 is, negative 1 cubed plus 6 is 5. Let's see here. 0 cubed is obviously 0 plus 6 is 6. 1 cubed is 1 plus 6 is 7. And 2 cubed is 8 plus 6 is 14. Now, take a look at the t-charts. So on the purple t-chart, I have negative 2 is a point, and I have that same point on the green t-chart. On the purple t-chart, I see that I have 5, negative 1, and on the green t-chart, I have negative 1, 5. Purple I have 6, 0. Green I have 0, 6. Purple I have 7, 1. Green I have 1, 7. Purple has 14, 2. Green has 2, 14. So guys, do you recognize that my x's and y's have simply switched places? Remember, that's what we said that an inverse function does. So take a look. For instance, I can say the domain of the purple function is, for what I've pictured, -2, 5, 6, 7, 14. Now, if I wasn't confined to just a t-chart, I would say the domain of the purple function is actually all real numbers, because the domain of any cube root function is all real numbers. But if I just am looking at the t-chart, well, notice the range of the green t-chart is -2, 5, 6, 7, and 14. So your x's and y's are reversed, so the domain of one function is the range of its inverse, and the range of one function is the domain of its inverse. That's all we're saying. Now, if I were to plot these points, what are we going to see? So on this, I'm going to keep my color coding, and I'm going to begin to plot the purple points. So I see -2, -2 is a point on this graph. 5, -1 is a point on this graph. 6, 0 is a point on this graph. 7, 1 is a point on this graph. And 14, 2, I can't move that onto my chart. What should I do? Oh, that's right. G of x is a cube root function. The parent function looks like this, right? And I know from transformations it's moved right 6. Oh, yeah. So I know, even though I don't have that final point to plot, I know what this function looks like, right? So even if I can't quite get it all on the screen, I have a good idea of the image anyway. Now I'm going to look at y equals x cubed plus 6. So -2 is on this point. Oh, those overlap. -1, 5. 0, 6. 1, 7. Oh, and I've got the same issue, don't I? 2, 14 goes out off the graph. Well, I know from the last one that if I look at the parent function, it's y equals x to the third. And I know that's that shape moved up 6. So I can generate my image. Oh, big dot theorem. Got a little bit off there. Even though I can't totally get it on the graph. Now turn your head sideways so you're looking along the yellow line. And do you see the symmetry between the graphs? So when I reverse the x's and y's in my equations and in my points, what happens is that the graphs become symmetric with respect to the line y equals x. So if I folded over that yellow line, my green and purple graphs should overlap each other perfectly. And any point that lies on the yellow line, like -2, -2, or 0, 0, or 1, 1, will be on both graphs. So that would be this point right here, right? -2, -2. Now I'm really fixing it with the big dot theorem. But that point should be on both graphs already. So now we know, and we could go back to the original list of objectives, the link between a pair of inverses both graphically and numerically. But remember, the whole big deal is you are simply reversing the x's and y's. So if we wanted to look at different ways that you could verify your work, okay, we know you can algebraically verify by doing something like f of x or f of f inverse of x and f inverse of f of x and work it out algebraically so that you get x both times. What if we actually look at our graphing calculator at different ways to verify? So guys, if you'll look at your graphing calculator, what I have done is say, well, my f of x was 3x minus 8, so I've inserted that in y1. For f inverse of x, I got 1/3 x plus 8/3, so I put that in the y2. In y3, I'm going to put the line y equals x because that's supposed to be my line of symmetry now. And when I graph all these, I'm in zoom 6, I can see that symmetry. I need to kind of tilt my head to the right, look up the black line, and I can see that the red and blue lines are truly symmetric to each other. But now, something else you can do is if you go to zoom square to where it's square, makes your screen a little more square shape instead of rectangular shape. It tends to make, for instance, your circles will look more circular instead of oval. On the rectangular screen, circles may not look exactly circular. But anyway, that might help you if you're having a hard time seeing the symmetry. Zoom 5 is an option. All right, so let's look at the same thing. We said earlier that y equals ln of x and y equals e to the x were inverses. So let's look at that. And I'm simply going to graph y equals ln of x. So whereas I'm turning my equal signs on, you go ahead and insert those. Remember, your ln x key is on the lower left-hand column of your calculator, and the e to the x key is above it. So when I zoom 5, I'm going to graph it. Now, you might go, wait a minute, that doesn't look right, Ms. Porter. Well, you saw an equation earlier. When the calculator needs to graph something that almost looks vertical, it kind of bugs out on us. So that pink graph really does come down, and whereas the green graph looks like it's almost horizontal right on the x-axis, that's not exactly right. That's just the best your calculator can show it. The pink graph should look almost vertical and overlap the y-axis, but your calculator doesn't graph that kind of thing well. So I can see that my exponential green graph and my logarithmic pink graph are inverses. I see this symmetry with respect to the line y equals x. All right, so now we're to the last topic. You can always reverse x's and y's and generate a new equation. You can always make a whole list of points on f of x, reverse the x's and y's, and generate a whole bunch of points on the inverse. You can always plot all the points for f of x and all the points for the inverse and see symmetry. But not every inverse is a function. So what we're trying to do now is determine, well, how can you tell quickly if a function has an inverse that's also a function? So let's use these graphs that I have right now, and let's use them for two purposes. Number one, to let us know when we have inverse functions. And number two, the big deal, or the other thing, is just to review graphing. Review your transformations. Review things we've already learned. So guys, on y equals the square root of x minus 5, I know that this is a square root function that moves right 5. So 1, 2, 3, 4, 5. I know basic square root functions go right 1 up 1. Not where I put that. Right 1 up 1. And right 1, 2, 3, 4 up 2. I'm using my 3 points on a function rule. So there we go. All right, now on the next one, I might need to do a little bit more work and say, oh, let's factor out an x. That gives me x squared minus 9. Oh, that's going to give me x plus 3x minus 3. Oh, I'll remember this. This is the cubic function where the right end goes up. I've got 0, 3, and negative 3 on the x-axis. And the graph looks like this, basically. It's not perfect. Oh, I think that function's odd, don't you? Do you see the symmetry with respect to the origin? Now, on my third graph, y equals 1/2 x squared plus 3, let's see here, I know is going to go up 1, 2, 3 to the vertex. Now, I can go out 1 up a half, but that's difficult to do. How about I go out 2? And remember, normally you go up 4 because 2 squared is 4. But I'm going to go out 2 from the vertex and up 2 because half of my vertical. So I'm using my vertical compression there, my vertical shrink. That is not where I graphed that. Let's try that again. So there's that graph. Now, on the next one, Do you remember that this is exponential decay? If the base of your exponential, the 1/2 to the x, if the base is somewhere between 0 and 1, it's got to be positive. But if it's less than 1, it's exponential decay, and then I move it down 3. So this is a little foreshadowing for things that we're going to be reviewing more later. So you may not totally remember this one, and that's okay. I'm going to get into it with you later. So the graph is going to look like this, and we will talk more about how to graph these later. So if you're not completely remembering that, never fear. All right, so here's what we're going to do. I'm going to show you a feature on your graphing calculator that allows you to always produce an inverse. All right, so what I'd like you to do is put y sub 1 equals the square root of x minus 5. Now do this with me, because if you watch me do it, you'll get really good at watching, but you won't remember how to do this for yourself. Even if you think you will, that's not really the way that works. Okay, so if I graph that, I'm going to go ahead and just zoom 6. You can see that function, and that looks like what we graphed earlier. Now, I want the calculator to draw the inverse for me. So I'm going to say, go to your draw menu. It's above the program key. So I'm going to say second, and then your program key. Second program is the draw menu. And do you see choice 8 is draw inverse? Now, I'm going to tell it to draw the inverse of what I've inserted in y sub 1, and that way I don't have to type in my equations again. So if I want to pull up y sub 1, I'm going to go to my variables menu, which is right beside the program key. I'm going to go to my y variables menu. I'm trying to draw the inverse of a function, so I just hit y1. Now, when I hit enter, it automatically draws the inverse for me. Now, is that inverse a function? Yes, it is. I can see that the inverse does pass the vertical line test. So I'm going to come back, and I'm going to say here that the inverse is a function. So inverse is a function. Now, I'm going to test on all of these. So let's look at the y equals x cubed minus 9x. So I'm going to go back to my calculator. You type in y equals x cubed minus 9x. I'm going to turn off my y1 and turn on my y2. And then I'm going to graph. So I see my y1. I'm not seeing it completely, but it's all right. I don't need to worry about seeing the max and the min perfectly. I've got the idea of the cubic function. So I'm going to go to my home screen, so second quit. I'm going to draw inverse, so second draw menu. Draw inverse is choice 8. Now this guy I think was in y2, so I need to pick up y2, so variables menu, y variables, function, choice 2 is y2. And so instantly I see the inverse. Whoa, that blue graph that just got drawn, that fails the vertical line test. So I'm going to come back over here and make a note that the inverse exists, but it is not a function. All right, so now I'm going to go to my third graph, y equals 1/2 x squared plus 3. You all insert y equals 1/2 x squared plus 3. While you're inserting, I will simply turn off my y3. Nope, I need to go back and turn on my y3. Turn off my y2. This should give you enough time to insert without having to pause the video. So I just inserted it as 0.5 x squared plus 3. When I graph it, of course, I knew that that looked like the pink parabola that shows. So I'm going to have the calculator draw the inverse. So second program, draw inverse, choice 8. Now this was in y4 if I'm remembering correctly. So I'm going to go to my y variables, function, y4 is choice 4, draw the inverse. Oh, again, the blue graph, that sideways parabola, fails the vertical line test. So I'm going to say the inverse is not a function on this one. So one last time, let's do y equals 1/2 x to the 1/2 to the x power minus 3. So you all insert y equals 1/2 to the x power minus 3. Notice it needs to be in parentheses. I'm going to turn off my y4 while you're doing that and turn on my y5. So notice the 1/2 is in parentheses to the x minus 3. When I graph it, I see that exponential decay, which has been moved down 3 units. I'm going to go to my draw menu, and then I'm going to say draw inverse as choice 8. And I believe I had that one in y5, didn't I? So I'm going to go to my list of y subs and choose y sub 5. And when my calculator draws it, whoa, the blue and green graphs are really, really close, aren't they? But the blue graph does pass the vertical line test. It sort of looks kind of vertical over on the left-hand side, but again, that's your calculator's inability to make that look better. So I'm going to come back and go, all right, on this one, the inverse is a function. Now, without having to constantly draw the inverse on the calculator, is there a way to look at the original function and say, yes, it is an inverse? Its inverse is a function, excuse me, without having to look at the inverse on the calculator? Yes, there is, guys. And it's called the horizontal line test. Any horizontal line on y equals x minus 5, that my function will never touch the horizontal line at more than one point. So y equals the square root of x minus 5 passes the horizontal line test, which tells me that its inverse will pass the vertical line test. Now, on y equals x cubed minus 9x, look, I mean, there's tons of places that I could draw a horizontal line here, and my blue function fails the horizontal line test because, look, my function is touching this horizontal line more than once. So if my original function fails the horizontal line test, its inverse will fail the vertical line test. So its inverse is not a function. Ditto on this second graph, okay? I can draw lots and lots of horizontal lines that the function crosses twice. So y equals 1/2 x squared plus 3 fails the horizontal line test. Therefore, its inverse fails the vertical line test and is not a function. On my last exponential decay function, it does pass the horizontal line test. So its inverse passes the vertical line test and is a function. So the idea here is that a function that is one-to-one has an inverse function. Whoa, whoa, I'm using vocabulary you've not seen. Guys, a one-to-one function, f of x, the official definition is that if a does not equal b, then f of a does not equal f of b. It's saying for every x value there is a distinct y value that no other x value gets to be mapped to. All right, that might be hard for you to visualize. So the bigger thing is that one-to-one functions pass the horizontal line test. So if you want to know if a function's one-to-one, then you can simply say the function passes the horizontal line test. And we know if a function passes the horizontal line test, its inverse passes the vertical line test. So the significance is that a function that passes the horizontal line test has an inverse that is a function. So the inverse always exists, but when I say f inverse of x exists, I'm saying the inverse exists and is a function. So let me show you a special example of this in action so we can start to talk about this. Now, if I start to graph my p of x, I know what it looks like. It's going to be a square root function that starts to the right 4. And I'm just going to do a quick sketch because I want to not sketch it perfectly but use the sketch to make a point with you. So I know that p of x is one-to-one because it passes the horizontal line test. Therefore, p inverse of x does exist. I'm going to go ahead and draw my y equals x line of symmetry. Okay. Now, what I need to do is say y equals the square root of x minus 4. Switch your x and y. Square both sides. Add 4. Now, since my original function passed the horizontal line test, I know my inverse passes the vertical line test. So I don't stop until I give it its function title. And then what I'm going to do is show you the graph. So I'll do this one in red. So I know that y equals x squared plus 4 is a parabola that looks like this. Again, I'm not being very precise. I just want to give you a general. Wait a minute. The red graph and the black graph are not actually mirror images over the line y equals x. So what's wrong? What's wrong is, guys, that I need to add a conditional statement here and say only the right half of the parabola is the inverse of the black square root function. So that requires me to say that the inverse equation is actually x squared plus 4 if x is greater than or equal to, look, its starting point here is 0, 4. So x has got to be greater than that 0. So sometimes you're going to have to work with the extra conditional statements that are actually part of the p inverse of x equation, or vice versa. So this is when things get a little bit harder than Algebra 2. You won't be able to completely function with algebra alone. You have to start incorporating what you know graphically. So if I look at q of x, I know that that's a parabola that moves left 3 and is upside down. So again, I'm not sketching a perfect graph. And then I've got the line of symmetry there. Now, the problem with this is, guys, that the original function is not one-to-one. It fails the horizontal line test. So this is something new that you've not seen us do. What I'm going to do is say, let me rewrite q of x as negative x plus 3 squared. Now, with a function like q of x that is symmetric with respect to a vertical line, I can choose, and this will become a more common practice, to negate half of it. And normally we negate the right half or the left half of it and keep the right half. So I'm going to put a conditional statement on there and say that x is greater than or equal to negative 3. So I'm just going from a negative 3, 0 to the right of that. Now I'm allowed to find an inverse. So this is kind of different too. I'm not going to work with the x is greater than or equal to negative 3 part right now. I'll come back and I'll get the conditional statement in just a second. So wait for a minute and I'll pull this together for you. So I switched my x's and y's. I need to isolate my new y, so I'm going to have to take plus or minus the square root of x. And that's going to give me, actually, plus or minus the square root of negative x, because I needed to move the negative first. That's going to give me y plus 3. And y is going to equal negative 3 plus or minus the square root of negative x. That's kind of weird. All right, so I know I can't have that plus or minus thing in a function. So I've got to decide, what do I do there? Well, let's use some symmetry. So I know that if I've got on this blue graph or black graph, that's negative 3, 0. I know 0, negative 3 should be on my inverse, right? Because I'm reversing x's and y's. Let's see here. I know that this point on my black graph would be right 1, down 1. So that should be the point negative 2, negative 1. So I know on my inverse I need -1, -2. So -1, -2. Oh, now I see that my inverse should look kind of like that. That gives me the symmetry I need, right? So what's that tell me? Well, it tells me that, keep in mind, this parabola, if you filled it out, would look like that. If I'm taking the top half of the parabola, then I use the positive. If I wanted the bottom half of the parabola, I would use the negative. Now, I'm going to say one more thing. Let me get rid of the dotted lines. I was just showing you that so you remember what the whole parabola looks like. This is what I like to say. If you have to have a conditional on the original equation, automatically put a conditional on the inverse. And that way, if you need it, it's there, and you won't get points deducted. If you don't need it, it doesn't hurt to emphasize it again. So you can see on my red graph that I start at this x equals 0 and go left of that. So x is less than or equal to 0. And then I've got the conditional. Now, I didn't really need it because if you're going to take the square root of a negative x, you've got to insert negative x's. You get like the square root of a -9 is the square root of 9. But I've got it. So this is our last example, and it's similar. If I look at y equals the absolute value of 1/2 x minus 3, I'm going to use some transformations. So if I just look at y equals 1/2 x minus 3, let's see, that is down 3, and then up 1 right 2, up 1 right 2, up 1 right 2. So that is this line. Now what I know is that when I put the absolute value on that, the low part of the line reflects upward. So it's going to look like that. So that's what my V shape looks like, and I'm going to erase. So notice, instead of graphing it like you learned to do in Algebra 1, I just graphed it using my absolute value transformation. So there's that. Let me erase this because I don't need it anymore. Now here's the deal. Can you see again that my absolute value graph is not a one-to-one function? It fails the horizontal line test. If I want to actually talk about its inverse, then I'm going to have to rewrite r of x and say, well, let's make it 1/2 x minus 3. And again, we generally take the right-hand half. So I'm going to leave the right half, and now I'm going to erase the left half. So that part that I took time to reflect winds up not being a deal. Oh, okay. Two things I'm noticing. If I leave the right half, the x is going to be greater than or equal to, let's see, this coordinate right here is 1, 2, 3, 4, 5, 6, 0. So that's for x is greater than or equal to 6. But wait. Instead of calling it a V-shaped graph at this point, isn't it just a ray? So can I make it even easier and say it's just a part of the line 1/2 x minus 3 if x is greater than or equal to 6. So that's going to be even easier to work with. And you might say, why would you do that? Because it's going to be easier for me to find the equation of the inverse. So now I'm going to start working with finding the equation of the inverse. When I work with that, I don't worry about the conditional statement. I'll come back and pick it up at the end. So let me multiply everything by 2, or you can add 3 first, either way. So that's going to give me y equals 2x plus 6. Now, I know lines are functions, so I'm going to go ahead and say, let me change this to red now. R inverse of x, I said change to red. R inverse of x is equal to 2x plus 6, and I've got to have a conditional statement, so I'm looking for something there. So remember I told you if your original function has some sort of a conditional, just plan on attaching a conditional to the inverse statement. All right, so let's see here. I've got my axis of symmetry. And what I need to do is just reflect the ray itself. So let's see here. The ray starts at 6, 0, so my inverse ray, 1, 2, 3, 4, 5, 6. Oh, I'm having a hard time reaching this. My inverse ray should start at 0, 6 and should kind of go up this direction. So let's see here. That means my inverse needs to be x is greater than or equal to 0 because I'm just going from 0, 6 to the right of that. Okay, so I've got it. Those are not easy. It's new. You've not had to do that kind of thing before, but this is something that we'll increasingly be doing throughout pre-cal.